Students. So today the topic that we're covering is the approximation from binomial distribution to normal distribution. So as we already know that binomial distribution is specific for a discrete random variable, and the normal distribution is caters to continuous random variable. So let's have a look at the graphical lookout for a binomial distribution. So for example, if I say that I have a variable that is binomially distributed, I'm saying I have a variable x which is binomially distributed and I'm doing 20 trials and the probability of success is 0.2. Now, when I calculate probabilities for every different value and I plot it against the probability density, just like frequency density, it is also a value that is plotted on the y-axis, probability density. For S1 level, you're not supposed to know it, but we'll cover it in S2. So probability density is plotted, and you can see that for different values, it is giving me different probabilities. So for the variable being 0, the probability is 0.011549. And for 1, this is the probability, and for 2, and then so on. And here you can find in our outer probability of between any range. There's a probability less than 8. These are the values that will add up, and you will get your cumulative probability, which is 0.9. So these are the values of probabilities that have been plotted, and this is the graph of binomial. Now, what happens if I increase the trials for any binomially distributed variable? Let me change the probability as well. Now, what happens when I increase the trials? If I increase the trials to 25, this is how the probability is plotted. I hope you're not getting confused with these lines. Right in or outer, it depends on if we need a cumulative probability. If we don't, just shut it down. And these are the probabilities for the different variables that we get. So what do you see as the number of trials increase? It starts taking the shape of a normal distribution. So when we have very large number of trials and we want to do a binomial distribution, we rather approximate it as a normal distribution and we convert it into a continuous variable and then we try to solve the question. I'll go to that part as well. But let's just increase the trials right now. What if I do the trials 30? What if the trials are 50? And so on. So what if the trials are 50? What if I say that there are 50 number of trials and the probability of success is 0.2? How do you find the mean? The mean is found by taking 50 times 0.4, which should end up as 50 times 0.4 is 20. And if I wanted to find the standard deviation, which is NPQ, sorry, the variance, which is NPQ, I'll just multiply this by points. We'll get that as well. Now, normally you'll find in different books that you can approximate a binomial to a normal when your value of NP is greater than 5 and NQ is greater than 5. In some books, they also say that NPQ is greater than 5. In some, they would say it is greater than or equal to 10, but we'll have a look at it around the values of NP or NPQ both. And the mean and the variance, to make it easy for you, you'll say when mean and variance both are greater than 5, then we can approximate a binomial to a normal distribution. How will we be doing that? When will we be doing that? I'll cover that as well. Don't worry. Let's just understand. So if I have a normal distribution, if I convert the same variable as a normally distributed variable, what two values do I need? I need the mean and the variance. So if I'm doing it for this case, I'll say it is normally distributed. My mean is 20 and my variance is 20. Now let's try to plot it on the graph and see that do the graphs give us the same response. So if I plot a normal distribution with mean as 20 and standard variance is 12, kind of a graph. Do you see it is almost replicating the binomial distribution? So this approximation is not just a mere fluke shot. It has this practical data backing with it. So when the number of trials are greater, you can approximate a binomial distribution with a normal distribution. Now there is just one part that remains, which is the continuity correction. For example, the question was asking me to find the probability of x less than equal to 18. So if I wanted to do the binomial distribution, I had to do x is 18 and then x is 17, and then I had to go back all the way until x is 0. This is how I would have had to solve it if I wanted to do it through the discrete random variable. I would have had to apply the binomial distribution 18 times. But what if I convert it into normal distribution? Now the normal distribution implies for a continuous variable, and that is where we need to do a continuity correction. So if I want to solve the same question by approximating this binomial distribution as a normally distributed variable, I will have to do a thing that is called continuity correction. And how will I do that continuity correction? So if I wanted to do this binomially, I would start from 18 and go all the way back to 0. There is an easy tool, an easy word that I tell students: take half extra. Whatever value you're starting from, whatever limit you're starting from, you take half extra. I am not saying greater, I'm not saying lesser. I'm deliberately using the word extra. So what does that mean? Starting from 18 and going all the way back to 0. So if you want to do it through a normally distributed variable, you'll say probability y. I've just given them different names so that it helps you understand. Y is less than or equal to, we know in normal distribution, equal to does not matter because it's just a single line and that does not represent any significant area. So instead of starting from 18.5, if I take half extra, I will, starting from 18, if I take half extra, I will end up on 18.5. And now I can solve this question just simply through a normally distributed variable. So this is a basic method of converting any binomially distributed variable into a normally distributed variable, and the conditions are that NP or NPQ both should be greater than 5. That is when we see it approximates well. What if the conditions would have been, what if the trials would have been less? What if there would have been only 20 trials? Then what? The mean would have been 20 times 0.4 is 8. And the standard deviation 8 times 4. See, it does approximate to a norm. Thoda sa you see there is just very minute little differences. And similarly, if I reduce the trial, the approximation would keep on getting worse. Let's change the norm. So the mean will be 20 into 0.3 is 6, and 6 into 0.7 is 6. So it does approximate. You see minute differences when the values are lower, and the lower the values are, or the lower the probability is lesser than 0.5, probability of success when it deviates from the value 0.5, the worse our approximation is. So approximation is suitable only for these cases when the trials are greater, when the probability of success is closer to 0.5. These are the conditions that makes the approximation successful. Now, a bit about continuity correction because it normally confuses a student. I'll give you a few examples as well. And a discrete variable with continuity correction. So if the question would have been probability x is less than 18, then what? Remember, we would have started from 17, then moved on to 16 and continued it till we would have ended up on. Now with continuity correction, I'll stick to the words that I've introduced earlier. Take half extra value. So if I'm calling it the variable y, I was starting from 17, going all the way back to 0. I'll take half extra, and that will be 17.5. Similarly, if I would have had probability x is greater than 32, then obviously I would have started from 33, moved on to 34, then all the way till n, the value is n. So if I wanted to do the continuity correction, taking half extra would mean I'm starting from 33. Think about the number line. I'm going till n. I'm taking 33, 34, 35, and if I take half an extra value, that means y is greater than equal to 32.5. That is half extra. Remember, I have to consider the probabilities of all these values and then add them up. So taking half an extra value of the variable, the continuous variable, the variable which was initially discrete, and we have approximated it to a continuous variable. This is what is called a continuity correction. So now, if I tell you x is between 10 and 39, I put an equal to 30. What would that mean? I would start from 11 and go all the way till 39. Now I have two limits that the question has told me. I'll take half extra with both. I'm starting from 11 and going all the way to 39. So taking half an extra at this end would mean 10.5. And ending on 39, taking half an extra from there, that would mean 39.5. So this is how the continuity correction goes. Similarly, if I take 5, x is between 5 and 18, then what? Now I would have started from 6, 7, 8, and gone all the way to 17. So taking 5 extra, 0.5 extra, half extra, 5.5 is where I'll start from. And 17 is where I was ending. So I'll take half an extra over there as well. And 17.5 is where I will end up. Just giving you another example. If I say I start from 9 and x is going all the way to 8, then what? Now I'll start from 9 if I wanted to do it through binomial, and I'll go all the way to 27. So taking half extra at this end would mean I'm starting from 8.5 and going all the way to 27.5, because that is where I will end up. I would have ended up on 27, taking half an extra from 27, I will end up on 27.5. This was the basic of approximation and the continuity correction.